In this video, let's have a look at the NC code of the pivot bolt. This code is fully handwritten, which is not very common in the industry, but for educational purposes it makes perfect sense. As a CNC machinist, it is essential to understand NC code. Best way to learn it is to write code manually. Why we need to understand NC code when I can use CAM? Answer is simple. Sometimes CAM programs have some errors in them, and when you clearly understand what is going on in the program, you can modify it on your CNC's controller instead of creating a new one with CAM software. To illustrate the program and give a better overview, a simulation software was used. Please note that the simulation is only to showcase different operations from the program. Important features, such as repositioning of the workpiece, have been removed, and some cycles are modified due to the differences between the Haas SL10 controller and the simulation software. To see the full program in action, please watch the manufacturing video of the pivot bolt. The code starts with a few comments. First we have the program number and a comment describing the part. Then we have the version of the program, when and by who it was created. Then we have the size of the stock. It reminds us to install bushings to the bar that is being fed into the spindle, otherwise the bar might start to throw and cause unwanted vibrations in the workpiece. And it also tells us what is the stick out from the spindle. In this case it is 115 millimeters. We always start our programs with moving to the home point of the machine. It is important because the machine might be in such coordinates that when we start the program it might crash into our stock. Additionally, we move 10 millimeters away from the x-axis 0 in case there are some tools in the turret that stick out a lot and might crash into the wall of the lathe when the turret is rotating. You'll see this piece of code in the end of every operation throughout the program. As you can see, first G28U0 means that we return to the home of x-axis. G28W0 means that we return to the z-axis home point. And finally, we rapid feed 10 millimeters in the negative direction of the x-axis. The program is divided to different sections. Each machining operation has its own section and a comment to tell us what the exact operation is done in the particular segment. First operation is setting up stock in G55 coordinate system. There is no tool in station number 5. We command it to a position, thus one can pull the plank firmly against it, as you can see in the video. We read in work coordinate system from G55 registry and rapid feed to Z8 and 10 to X80. M0 is program stop. We use it a lot in this program. In this case, it is to stop the machine in order to pull the stock against the face of the turret. After the stock is set up correctly, we move away 5 millimeters in Z-axis and return to the home point of the machine. Second operation is face turning. Here we perform the facing operation in a little bit unusual manner. Instead of most common C-type insert, we choose to utilize the grooving insert together with the grooving cycle G75. We rotate the turret to position T6. 15 marks the tool offset registry from where the offset is read in. Since Haas SL10 lathe has only 12 tools in the turret, the rest of the tool numbers in the registry can store alternative offsets for those 12 tools. In this program we use this grooving insert, but sometimes it is measured in from the right side. The tool name is also added as a comment to clarify the code. We start the spindle clockwise at a constant turning speed of 1500 rpm. Then we limit it to 2100 rpm. Starting the spindle is always done before any movements. That way, if the tool crashes into the workpiece, it starts cutting instead of being just pressed against the workpiece, and there is some chance that it can survive. Crashing into a stationary workpiece usually ends up with a broken insert due to the brittle nature of carbide. We rapid feed to position Z3 in G55 work coordinate system. Moves are done one axis at a time, just to make it easier to predict the movements that the machine is making. If there are any miscalculations in the positioning, and the machine rapid feeds in multiple axes, the operator doesn't have a clear view of the final position of the movement and might not press the emergency stop button early enough. We start the coolant with M8, it is followed by G75 grooving cycle, and finally we return to home. There is a program stop at the end of almost every operation. That way we can open the doors and check if everything is done as intended, and run the operation once more with modified parameters if needed. Once we have verified that the program works correctly, we can remove those lines. Next operation is center drilling. We rotate to position T9, start the spindle with constant turning speed, rapid feed to a nearby position to the stock. Then we move to X0, slightly touch the stock, and start G82 drilling cycle. After the cycle has completed, we return to home and stop the program. Now we move on to setup number 2. Bar stopper is now called out according to G54 work coordinate system. It also means that all operations in this setup are carried out in this coordinate system. After this, we need to install the tailstock. The 2 previous operations were basically preparations for this. Now that the stock is sticking out from the spindle more than the length of the part, we can start machining the geometry of the part. Once again, we rotate to position T5, which is left empty. We rapid feed to this position, to what length the stock needs to be sticking out from the spindle. We stop the program so the operator can open the doors and pull the stock firmly against the face of the turret. After that is completed, we move away 5 mm in Z-axis and then return to home point. And finally we have a comment telling us to engage the tailstock. First operation in this setup is outer diameter roughing. G71 roughing cycle together with G70 finishing cycle is the bread and butter of longitudinal turning. Make sure you understand them in great detail. We start with the tool change, we start up the spindle, rapid feed to nearby position to the part. We turn on the G42 tool nose radius compensation, switch the spindle to G96 constant surface speed mode. The S value is given in meters per minute, as before it was rotations per minute. G50 is very important here to avoid unnecessarily high spindle speed. G71 roughing cycle, the contour of the outer diameter is described after this line. Line N10 marks the beginning and N20 the end of the contour. What makes G71 very useful is the fact that once we have defined the contour, we can use the same line numbers in G70 finishing cycle as well. No need to repeat the code. Once the cycle is complete, we turn off the tool nose radius compensation and move to the home point and then stop the program. Next up is groove roughing. Commonly grooving is performed as plunging along the x-axis. Here we take the grooving tool and run it as a turning tool to establish the groove-like feature. This time we read the offsets from register 16. We start up the spindle, rapid feed to nearby position, start the coolant, switch to constant cutting speed, feed into the material and start machining along the x-axis. Once the machining is complete, we move away from the workpiece and return to home point. We move on to outer diameter finishing. Here we utilize the G70 finishing cycle. All the steps are basically same as with every other operation. Next up is diameter 18.5 groove finishing. Then we move to diameter 17 groove finishing. Next operation is radius 3.5 fillet roughing. We simply plunge the grooving insert to the material. The actual fillet is created with the finishing pass. Here we have the fillet finishing. Using GO2 we create the desired geometry with 3 different moves. Once that is completed, we return to the home point of the machine. We have few comments to remind us to remove the tailstock as we're getting ready for setup number 3. Third work coordinate system is used to make the thread turning as stiff as possible. So far we had stock sticking out from the spindle a lot. To ensure a good quality thread, we are taking that stock and moving it in a little bit, as the thread is only in the front part of the bolt. Now we move on to the threading operation. We rotate to position 12 and stop the program. This stop is needed to install the coolant hose. As already mentioned in the beginning, items that stick out from the turret a lot get stuck between the turret and the wall of the machine. As this coolant hose is made from plastic, basically is being broken off from the turret, and to avoid that we install it only when needed. Once the hose is installed, we read in the correct offsets from register 12, start the spindle, rapid feed to nearby position, switch to constant cutting speed, start the coolant, and then run the G76 threading cycle. It is arguably the simplest to code, but it lacks sufficient control according to others. After this operation, we need to remove the coolant hose. During thread turning, some burrs may have been created at the tips of the thread that could cause problems at the assembly. In this step, we simply clean those off by running a finishing insert along the tips of the thread. We move on to setup number 4. Once the stock has been set up the right way, we need to engage the tailstock. The first operation is diameter 22 outer diameter finishing. Here we finish the diameter that was used to hold on to the part while we're cutting the threads. Next up is diameter 18.5 cone turning, 5 degrees. An additional feature that was established during the development process for the ease of assembly. It's not shown on the drawing on purpose. It is to show how part development is a dynamic and iterative process. After this, we need to remove the tailstock as we are getting ready for the cut of the part. First we call out the correct tool, the grooving insert from station number 6. We start the spindle, limit spindle speed, rapid feed to a nearby position, and turn on the tool nose radius compensation. We switch to constant surface speed and then feed into the part. First we are creating this relief for the chamfer. Once that is being complete, we move away from the material a bit forward in Z-axis, and then we do this diagonal move which creates this chamfer. Once the chamfer is being complete, we proceed to the cutoff of the part. Once the cutoff is completed, we switch off the tool nose radius compensation, return to the home point, and then M30 end of program. That was the NC code of the pivot bolt.